Hey, welcome back to Math with Patrick and Quill. Today is November 25th, and we're solving problem 329 from the Daily Epsilon calendar. And we should show why the answer today is 25. So we're just trying to find the least number of coins among pennies, nickels, dimes, and quarters that would add up to $4.99. So pennies are worth 1 cent, nickels are 5, dimes are 10, quarters are 25, and we're essentially just trying to create 499 cents as our target number. Now, I think I'll just do like the easy strategy, which is just to fit as many of the big thing as I can into this number. And when I can't any longer, I will try to fit as many dimes as I can, then nickels, then pennies. This I would call a greedy algorithm just because I'm trying to do the biggest number possible first. And I don't think my strategy is going to be wrong in any way because either these numbers are just multiples of each other, or they're not multiples of each other, but they have enough common factors that I don't think that only doing 25s to begin with is going to mess up anything. Waiting to do tens until I must. Now, if these numbers were different values, then this greedy algorithm might fail. And so I think that's going to be an interesting scenario. I might want to create one just to show what I mean, but for now, let's just try to solve the problem. For every 100 cents, I'm going to do 4 quarters. And so 200 cents is 8 quarters, 300 cents is 12 quarters, and then finally 400 cents is 16 quarters. Now I can't do 4 more quarters because that's too much, but I can do 3 more quarters and I get to 475. Now my plan is just to add some dimes until I can no longer. So we can add a dime, that's 485. We can add another dime, that's 495. So that was 20 coins and then 21 coins. And then finally, our last 4 pennies lets us get to 499 cents or $4.99. And that will increase our coin total by 4, getting 25. So there's our answer for the day. Let me show you, or let me create that example. It'll take me a sec, but I want to show you what I meant by maybe a greedy algorithm wouldn't work. The way that I figured out what numbers might show a good example is essentially getting some numbers that don't really have any good common factors or numbers that aren't multiples of each other. So I figured that primes and then the number 1 would be a good example to show that sometimes this greedy algorithm of just picking the biggest one until you can't anymore isn't always the best or most efficient strategy in the end. And then I'm also picking a very specific target number of 60, just because, again, in creating this example, I know that 13 plus 17 equals 30. And so it's really clear to me that we should just do 13, 13, 17, 17 to create the number 60 here. However, with my greedy algorithm, where I only care about adding the biggest thing possible until I can no longer, I will do 17, 17, and then 17 again. This number right here is 30 plus 21, so 51. And at this point, I can no longer add another 17, nor can I add a 13 because I do go over 60. So I would be forced into adding on 9 ones. So all these ones. And then with this greedy algorithm, I had 3 17-cent coins and 9 1-cent coins. So overall, this strategy gave me a 12-coin solution when 4 is the most efficient. In any case, this greedy strategy did not kind of hamper us in finding our solution for today's problem, probably because coins are set up in such a way where we're allowed to think in kind of this greedy manner of thinking of the biggest one and working our way down. I feel like our system is designed in a certain way that allows for it to be used easily. Whereas a system with prime numbers and pennies, but prime number coins would be a little bit harder to use in practice. So anyhow, I think I'm all done for today. Thank you for watching, and I'll see you tomorrow. Bye.